Static fluid, visual and audio media. Members of the seventh group there are Eltera, Bibi Kavana, Gwen Aditya, and Tracy Fabrina. Static fluid, often referred to as fluid statics or hydrostatics in English, is a branch of fluid mechanics that studies the behavior of fluids when they are at rest or not moving. In this condition, the fluid is in a state of static equilibrium, meaning that the forces acting on the fluid elements are balanced so that there is no flow or acceleration of the fluid. In physics, for scientists and engineers explain that static fluids are fluids that do not experience flow, so that every part of the fluid is in a state of equilibrium. In this condition, the fluid can still receive external forces, especially gravitational force, which causes pressure at every point within the fluid. This pressure acts in all directions, and its value depends on the depth of the fluid, the density of the fluid, and the acceleration due to gravity. Hydrostatic pressure. Hydrostatic pressure is the pressure exerted by a stationary fluid due to the weight of the fluid itself. Key characteristics: pressure increases with depth, not affected by the shape of the container. On this slide, several illustrations are presented, including fish and a diver underwater, a ship on the surface, and a formula triangle. The illustrations of the fish and the diver are used to represent the concept of depth. From these images, we can understand that the deeper an object is submerged in a fluid, the greater the pressure it experiences. This occurs due to the accumulation of fluid mass above the object. Meanwhile, the illustration of the ship demonstrates that hydrostatic pressure does not only act on objects submerged in the fluid, but also on objects at the surface. The formula triangle serves as a visual aid to understand the relationship between pressure, density, gravitational acceleration, and depth, expressed in the equation P equals to rho GH. Therefore, all the illustrations on this slide are intended to strengthen conceptual understanding of hydrostatic pressure through contextual visual representation. Properties of hydrostatic pressure. First, the magnitude of fluid pressure is the same in all directions. Second, the magnitude of fluid pressure at the same depth is the same. Third, it depends on gravity. Fourth, it depends on the density of the fluid. Fifth, it does not depend on the shape of the container. And the last, the deeper an object is from the water surface, the greater the pressure. On this slide, there is an illustration of a container filled with fluid, with several holes at different heights, showing water jets at varying distances. This illustration is used to demonstrate that hydrostatic pressure depends on depth. The deeper the position within the fluid, the greater the pressure, which is indicated by the farther water jet from the lower holes. In addition, this illustration supports the concept that pressure in a fluid acts in all directions and is independent of the shape of the container. Instead, it depends only on depth, fluid density, and gravitational acceleration. Thus, the image functions as visual evidence of the fundamental properties of hydrostatic pressure discussed theoretically. Learning objective. Students are expected to be able to connect the concept of hydrostatic pressure with phenomena that occur in the surrounding environment. On this slide, several applications of hydrostatic pressure are presented, including Submarines made of metal can float on water because their specific gravity is greater than that of water, and humans cannot dive deeper than 120 meters due to the immense hydrostatic pressure of the water. And the last, the infusion is always higher because the position of the infusion is adjusted so that the pressure of the flow and infusion fluid is greater than the blood pressure. The shape illustration shows how pressure in fluids contributes to the floating behavior of large objects on water. The diver illustration represents how pressure increases with depth, which explains why humans have limitations when diving due to increasing pressure. Meanwhile, the four infusion illustrates an application in the medical field, where the fluid container must be placed higher than the patient's body so that the fluid can flow due to the pressure differences. Therefore, these illustrations highlight that hydrostatic pressure is not only theoretical concept but also widely applied in everyday life. Density. Learning objectives. Students are able to analyze the relationship between mass, volume, and density and their effects on objects floating or sinking in fluids. What is density? Density is a property possessed by materials. Density is defined as the ratio of mass per unit volume. And the last, the greater the density, the greater the compactness of the object. There are illustrations of objects such as cork, wood, and metal placed in water. These images are used to demonstrate differences in density, which determine whether an object floats, suspends, or sinks in a fluid. Objects with lower density than the fluid will float. Objects with similar density will remain suspended, and objects with higher density will sink. This concept is expressed by the equation ρ equals to m per v, which defines density as the ratio of mass to volume. Therefore, the illustration helps to explain the relationship between density and the behavior of objects in fluids in a more construed way. Density can be used to determine whether an object will float on water. Objects with a lower density will always float above those with a higher density. For example, oil will always float on water because its density is lower than that of water. All objects with a density greater than that of water will always sink. This principle is used by naval architects in designing ships. Observe the image below. This principle is used so that submarines can dive and resurface. On this slide, there are two images that explain the concept of density. In the image on the left, we can see a mixture of oil and water in a glass. The oil stays on top, while the water is at the bottom. This happens because the density of oil is lower than the density of water, so oil floats above water. Next, in the image on the right, there is an illustration of a submarine in three different conditions. The first is floating, where the density of the submarine is lower than water, so it stays on the surface. The second is neutral buoyancy, where the density of the submarine is equal to water, so it remains suspended in the middle. And the third is sinking, where the density of the submarine is greater than water, causing it to go down. From these two images, we can conclude that the position of an object in water depends on its density. If the density is lower, the object will float, and if it is higher, the object will sink. Archimedes' law. I'm sure you've all experienced that feeling when you step into a swimming pool and your body suddenly feels so much lighter, right? Well, that's not just in your head. There's actually a solid physics explanation behind it. And that's exactly what we're going to talk about. So, Archimedes' law states, an object that is partially or completely immersed in a liquid experiences an upward force equal to the weight of the liquid displaced by the object. In simpler terms, any object submerged in a fluid, whether partially or fully, will experience an upward force whose magnitude equals the weight of the fluid it displaces. This upward force is what we call the buoyant force. Now, if we look at the illustration on this slide, there are three beakers containing different objects. The first one shows an object floating partially above the surface. The second one is submerged a bit deeper, and the third one sinks completely to the bottom. This tells us that how an object behaves in a fluid really depends on how the buoyant force compares to the object's outweight. Mathematically, the buoyant force is expressed as Fa equals to rho point G point V, where Fa is buoyant force measured in newtons, rho is density of the fluid measured in kg or m pangkat 3, and G is gravitational acceleration measured in m per s squared, and the last V is volume of fluid displaced measured in m pangkat 3. So, the bigger the submerged volume and the denser the fluid, the greater the buoyant force acting on the object. It's a simple concept, but incredibly powerful in its applications. Okay, that's us learning objectives of Archimedes' law, which is students are able to determine the condition of an object floating, hovering, or sinking based on the comparison of the density of the object and the fluid. As we can see in this slide, when an object is immersed in a liquid, there are three possibilities. It will sink, float, or remain suspended. First is sinking. An object sinks when its position is always below the surface of the fluid. This happens when the density of the object is greater than the density of the fluid, or rho object is bigger than rho fluid. In this case, the weight of the object exceeds the buoyant force, or Fa. So, the base of the container provides a normal force to support it. The equilibrium condition is V equals to N plus Fa. Second is hovering or suspended. An object hovers when it stays somewhere between the surface and the bottom, neither rising nor falling. This happens when the density of the object is equal to the density of the fluid, or rho object equals to rho fluid. Here, the buoyant force is perfectly balanced with the object's weight. V equals to Fa. And the third, floating. An object floats when part of it sits above the fluid surface and part of it is submerged. This happens when the density of the object is less than the density of the fluid, or rho object is smaller than rho fluid. Only a portion of the object's volume, or V2, displaces fluid, not the entire volume. The equilibrium condition is still V equals to Fa. So, the key takeaway here is all about density comparison. That single factor determines what happens to an object the moment it's placed into a fluid. Okay, now we're on the third slide of Archimedes' law, and honestly, this is the most exciting part because here we talk about real-world applications of Archimedes' law. The learning objective of this slide is for you to be able to connect Archimedes' principle to various everyday phenomena. This slide presents three great examples. First is submarines. Submarines are probably the most iconic application of Archimedes' law. A submarine has ballast tanks that can be filled with seawater or emptied and filled with air. When the tanks are flooded with water, the submarine's overall density increases, allowing it to dive. When the water is expelled and replaced with air, the density decreases and submarine rises back to the surface. This mechanism allows submarines to dive, hover, and float as needed, all by controlling density. Second, hot air balance. Hot air balance work on the same principle, except the fluid here is air rather than water. The air inside the balloon is heated, which causes its density to become lower than the density of the surrounding atmosphere. As a result, the buoyant force from the outside air exceeds the total weight of the balloon and its passengers, causing it to lift off the ground. Once the heating stops, the air inside cools down, its density increases, and the balloon descends. And the third, which is the last, boats and ships. For boats and ships, the principle is that the buoyant force acting on the hull is proportional to the weight of the vessel. That's why a steel ship weighing thousands of tons can still float, because its hollow hull displaces an enormous volume of water, generating a buoyant force large enough to support the entire weight of the ship. So, connecting all three slides together, Archimedes' law isn't just abstract theory, it's working all around us, from submarines deep in the ocean to hot air balloons drifting through the sky. The key to understanding it all lies in grasping the concept of density and buoyant force and how they interact with each other. Okay, now we already end the part of conclusion of this visual media. So, the conclusion is, fluids are substances that can flow consisting of liquids and gases. In their study, fluids are divided into static fluids and dynamic fluids. Static fluids study fluids at rest, where hydrostatic pressure is influenced by density, gravitational acceleration, and depth. The deeper an object is in a fluid, the greater the pressure it receives. Important principles in static fluid include Pascal's law, which states that pressure is transmitted equally in all directions, and Archimedes' principle, which explains that buoyancy is equal to the weight of the fluid displaced by an object. Meanwhile, fluid dynamics studies fluids in motion, with key concepts such as the continuity equation and Bernoulli's principle, which explains the relationship between flow velocity and pressure. Overall, fluid concepts are very important because they are widely applied in everyday life, such as ships that can float, hydraulic systems, water flow in pipes, and even the working principle of aeroplane wings. Okay, I think that's all about the visual media from the 7th group. I'm sorry if there's any mistake, so thank you for watching and see you next time.